Here is a quiz problem. Write a function that adds up all the odd integers between two endpoints, a and b, including the endpoints themselves. Before you touch the keyboard, stop. The best first move is not to write code. In this video, we build that function the way a professional would. Plan on paper, solve a simpler version first, catch a bug, then add the final twist. One worked example, start to finish. Start with the outside of the function before any logic. First, a good name, some odds. Second, the inputs. We have two endpoints and we want everything between them, so the inputs are those two endpoints, A and B. Third, what does it hand back? A single total, so we keep a variable called sum of odds and return it at the very end. That gives us a skeleton, a name, two inputs, and a value to return. The middle is still empty. Now resist the urge to code. Take a piece of paper first. Do not solve it the way a human does, glancing and just knowing the answer. Think about a recipe a computer could follow. Should it loop? Should it use a conditional, a for loop, or a while loop? Try the simplest example. Let A be 2 and B be 4. Write the numbers 2, 3, 4 in a row. These are the numbers to look at, one at a time. That is your plan. Do a second harder example so you know the answer before writing any code. Let A be 2 and then B be 7. Write 2, 3, 4, 5, 6, 7. Now walk through them one at a time. 2 is even, skip it. 3 is odd, add it. 4 is even, skip. 5 is odd, add it. 6 is even, skip. 7 is odd, add it. We add 3 plus 5 plus 7, which is 15. That is our target. And for the simpler example, 2 to 4, the only odd number is 3, so the answer is 3. We now know both answers in advance. With both answers in hand, still do not write the full solution. A big problem can hide edge cases, so solve a simpler cousin first. Instead of summing only the odd numbers, sum every number between A and B. Get that working completely. Once it does, adding the odd rule is a tiny tweak. This is incremental development. Build a little, test a little, then grow. Summing every number sounds like a loop, because on paper we touched each number in turn. Start with a for loop. Write for I in range of A to B. Before the loop, initialize the total. Sum of odds is set to 0. If you forget this, the editor complains that the variable does not exist yet. Inside the loop, as each I appears, add it to the running total. At the end, return sum of odds. That is the whole for loop version. The same job with a while loop takes a little more care. A while loop does not create its own counter, so you must do 3 things by hand. First, initialize the loop variable. I is set to A. Second, write the condition, while I is less than or equal to B, which includes B itself. Third, inside the loop, remember to increase I by 1 each pass or the loop never ends. The body is the same. Add I to the running total. Miss the increment and you get an infinite loop. Time to test with the simple example 2 and 4. The while loop gives 9, 2 plus 3 plus 4. But the for loop gives 5. They disagree, so something is wrong. The culprit is range. Range of 2 to 4 produces 2 and 3, but stops before 4. It goes up 2, but not including the second endpoint. If you had not spotted it, a print statement inside the loop would show the numbers being added. First 2, then 3, and never 4. The for loop silently skipped the last number. That is a classic off by 1 bug. The fix is small. Change the end of the range from B to B plus 1. Now range of 2 to B plus 1, that is range of 2 to 5, produces 2, 3, and 4, including the endpoint. Run it again. The for loop now gives 9, matching the while loop. Both agree, so the sum all version is correct. This is why testing early pays off. The bug surfaced on a tiny example, not on real data. We solved the easier problem completely before adding any extra logic. Now the final twist, only the odd numbers. We add I to the total only when I is odd. There are 2 clean ways to say that. One reuses the function we already wrote. if not is even of I, because is even returns true for even numbers. Not is even is true exactly when I is odd. The other checks the remainder directly. If I mod 2 is equal to 1, since an odd number leaves a remainder of 1 after dividing by 2. Either guard goes just inside the loop, wrapping the line that adds to the total. Test against both paper answers. Some odds of 2 and 4 should be 3, the single odd number in that range, and the code returns 3. Some odds of 2 and 7 should be 15, from 3 plus 5 plus 7, and the code returns 15. Both match the paper exactly. The while loop version, with the very same odd check added inside it, returns the same totals. By solving a simpler problem first and adding one rule at a time, we reach the correct function without wrestling a whole tangle of bugs at once. Step back and see the method. Solve a simpler problem first, then add functionality a little at a time as new nuances appear, instead of writing one huge block and drowning in errors. Test often on small examples where you already know the answer. To see what your code is really doing, drop in a print statement, or step through it with Python Tutor, a free visual debugger. Testing early and debugging with print or Python Tutor will save you again and again. Want practice? The lecture file leaves 3 functions for you to write yourself. Is palindrome, keep consonants, and first to last diff. Read each specification, its contract of inputs and outputs, and try to write code that matches it. The answers are in the file, but solve them on your own first. Writing a function from its spec is the skill this whole lecture builds toward. To close, why functions matter. A function abstracts away a useful task, a piece of work you might reuse many times across a program. It takes inputs and hands back a return value. And creating a function is not the same as running it. You write the function once, but you can call it as many times as you like. That single idea, define once and use everywhere, is what makes code easy to write, read, debug, and change. Small, well-named, well-tested functions are the building blocks of robust programs. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.